In this video we take a closer look at the state-machine replication mechanism of the Internet computer. But before we dive into this topic, let's briefly explain what the Internet computer is. The Internet Computer Protocol, ICP for short, is a protocol that coordinates node machines in independent data centers to provide a compute platform that can host any software. Applications hosted by ICP run as canisters, which hold both the code and the data of applications. These canisters process messages from users and other canisters, changing the state of the canister. In other words, the Internet computer is a network of replicated state machines. The inputs are request messages from users or other canisters. The outputs are the response messages, and the canister method code describes the state transition. To cope with malicious behavior, all outputs from the state machine are threshold signed. In this video, we'll look into the details of how this replication is achieved with ICP. The protocol can be divided into 4 layers. While the lower 2 layers are responsible for message dissemination and agreeing on their order despite potentially malicious nodes, the upper 2 layers ensure deterministic processing. Consensus delivers blocks with messages for canisters to message routing, which in turn ensures the messages are enqueued at their destination canister so they can be processed by execution. When messages are executed, the whole network transitions to the next state. The protocol has been designed to cope with up to F malicious nodes. F must be smaller than a third of the nodes. Let us follow a message from a user. First, it is in status unknown, until the nodes agree to have validated and ordered it, and consensus hands it over to message routing when its status is turned to received. When message execution has started, the status is processing. When a response has been computed successfully, the status becomes replied. At any point in time, the status of any message can be changed to rejected, if either the protocol or the canister decide not to continue working on this message. Let's look at the data structures for a canister A. There are separate input queues for each canister from which A receives messages, and there is one queue for user-generated messages to A. There is an output queue for each canister that A sends messages to. In addition, there is the ingress history, which stores messages from users as well as their status and responses. Users can query the ingress history of the subnet to learn about the status of their message. When message routing receives a finalized block, it extracts the messages from the block and inserts them into the corresponding queues of the respective canisters. Next, the execution environment takes these queues and the canister state and processes some messages from the queue. The execution of these messages must be deterministic, so all nodes end up with the same state. After execution, processed messages are removed from or added to queues, the ingress history is updated, and the replicated state of the relevant canisters is modified. Note that in a crash recovery model without Byzantine behavior, users can trust any node to report on the status and response of a message correctly. In our environment, more diligence is needed. Instead of requiring a user to ask at least F+1 nodes what the correct response is, the protocol provides a threshold signature over the whole subnet state. To this end, the replicated system state for a given height can be represented as a Merkle tree with the state of the canisters and the input and output queues as leaves. After executing a block and computing this Merkle tree, the nodes broadcast a signature share of the Merkle tree root hash. A node needs to receive 2 F+1 such certification shares to combine them into a state certificate. The certified state is used in several ways in the IC. Its main purpose is output authentication. Users rely on signatures constructed from certificates on ingress history responses. In addition to verifying responses from canisters, the certified state is also used internally to detect and mitigate non-determinism and keep the duration of execution and consensus rounds aligned. To achieve this, consensus adds the highest height for which a node has a valid state certificate. Other nodes consider a block valid only if the node's locally available certified height exceeds the certified height in the block. We've now seen how a message goes through the Internet Computer Protocol and how a user can trust responses from the Internet computer. However, there is a small problem due to asynchrony. Imagine an application where a user submits a token transfer message to a canister to pay another user for some service. Is it safe to submit another transfer message after waiting for 5 minutes without seeing the ingress history reporting any certified status? Clearly, the user doesn't want the transfer to be executed twice. This is solved with the following modifications to the protocol. Every message from a user contains an expiry time. The block maker inserts its current local time in the block, together with messages from users and the node's certified height. The other nodes in the subnet only notarize a block if the block's time is higher than the previous block's time and at most the node's current local system time. The expiry time of all messages from users exceeds the time in the block and it is at most delta greater than the time in the block. As long as all nodes are synchronized well, this guarantees correct nodes can create and validate blocks from other correct nodes. Time is added to the replicated system state at every height and then certified. Thus each subnet has its own time, which increases strictly monotonically together with the certified height. Execution of a message is only started if the current subnet time is below the expiry of message from a user. Together, these modifications ensure that every message from a user enters the state processing exactly once before its expiry time or it will never be executed. The last part of this video explains how ICP achieved scalability. Instead of executing every message for every canister on every node, the set of canisters is partitioned across subnets. That is, the protocol groups the nodes into disjoint sets. Each set of nodes works together to provide state machine replication for the canisters they are responsible for. Note that canisters on different subnets can exchange messages with each other as well, so this doesn't just parallelize the execution. Each subnet runs its own consensus instance and the subnets create a network of state machines. To this end, messages in output queues for canisters on other subnets are ordered into so-called crossnet streams, one for each subnet canisters communicate with. These streams are then also part of the replicated state and are certified as described earlier. At the end of processing a block's payload, nodes then exchange certified streams with nodes from other subnets. This allows consensus to use these streams to agree on messages from other subnets. When the consensus layer creates blocks, messages from these streams are included into the blocks, next to the messages from users. Before notarizing a block, a node checks the signature and if no message from the stream was skipped. Since all the signatures are based on a threshold of 2f+1, a malicious node cannot convince a correct node to accept an invalid message. In summary, thanks to these mechanisms, users can be assured that responses from the Internet computer have been created by honest nodes, and unauthorized tampering of canisters is prevented. As a consequence, the Internet computer is a secure, efficient and scalable platform for running all kinds of applications. Thanks for watching.